In this problem, we're going to work a combustion analysis problem where we can determine the empirical and molecular formula of a compound. Now, remember, all of the carbon is converted to CO2, hydrogen is converted to water, and you find the oxygen in this case. It can be nitrogen, sulfur, any other element by subtraction from the other two. So I know this is a combustion analysis problem because it says combustion analysis, which that's really the best way to tell it apart. If it doesn't say combustion analysis and it just says percentage, then that's the percent comp, and that will be the second problem worked. But the combustion analysis are very common with organic compounds, and they're easy to do. They just require an extra couple steps from the percent composition. So as we line this up, I'm going to run carbon. So we'll start there. We're going to start with 0.922 grams I've got missing 1 grams of CO2. And we know that for every 44.0095 grams of CO2, we have 12.0107 grams of carbon. Now remember, these are calculated in this case from the periodic table, and any molecular compounds are the sum of the elements from the periodic table, so elemental masses. Okay, so when we do this, we produce 0.2516790 grams. Do you have to keep all the digits? You have to keep quite a few. I tend to stick with at least 4 places after the decimal because some of these numbers can get very small and you don't want to lose something important. So the next one is hydrogen. I'm going to start hydrogen and I'm going to work it all the way left to right. It's 0.1573 grams of water. And we know that for every 18.01528 grams of water, we're going to have 2.01588 grams of hydrogen because there are 2 hydrogens per every water molecule. That leaves us with 0.0176017 grams of hydrogen. Now oxygen is going to come out by default. We're going to start with the total mass, which is 0.381 grams. We're going to subtract the grams of carbon, which is 0.2516790, and we're going to subtract the grams of hydrogen. This grams of hydrogen, so that leaves us with 0.111718 grams of oxygen. Now, what I have done is set them up so we're rolling this way. So this is all the carbon, this is all the hydrogen, and this is all the oxygen. At this point in time, we can't compare grams because each element does not weigh the same, but we can compare moles. So we're going to convert everything to moles. So we know that there are 12.0107 grams of carbon per 1 mole. So that gives us 0.020955 moles. For hydrogen, we go back to 1.00794 grams per 1 mole because we're only dealing with 1 mole. So we have 0.0174630 moles. And for oxygen, we're dealing with 15.9994 grams per 1 mole. So that leaves us with a whopping 0.00698 moles. Now we want the smallest ratio, so we're going to divide by the smallest number. of moles. In this particular case, it's going to be 6.98264 times 10 to the minus 3, which is the moles of oxygen. Okay, it doesn't matter which one it is, you pick the smallest. That being the case, we do the math. We get 3.00. We get 2.501. And we get 1. Now this is, remember, it's carbon, hydrogen, and oxygen. However, we can round 0.1, and 0.0, which we have here, but we can't round 0.5. So we're going to multiply everything by 2. That will give us 6 carbons, 5 hydrogens, and 2 oxygens. It brings us down to, we've got ratios here, so we now know that the empirical formula is equal to C6H5O2 because we have a ratio of each one. Now, that means that we're given, the additional information we're given is the mass of the molecular compound. We may also be given the number of atoms present. So if we calculate the empirical weight, which is I'm just going to approximate because we don't have a good number, so if we calculate it, we get about approximately 109 grams per mole. Well, if we look at that, we know that 2 times the empirical weight equals the molecular weight, because 109 times 2 is about 218, which falls into the range. So if that's the case, then 2 times the empirical formula will equal the molecular formula. So the molecular formula is going to be equal to C12H10O4. In this particular case, the problem asks for both the empirical formula and the molecular formula. So remember, even if the empirical formula and the molecular formula are the same, you have to identify them. So this is how you work a combustion analysis problem, solving for the empirical and the molecular formulas of a compound. But remember, if then this one we're given the molecular weight. If we're not given the molecular weight, but we're told that we have 10 hydrogens, then you know that the empirical formula is multiplied by 2.